Welcome back to my lecture series on columnar structures of spheres. First of all, I'm happy to announce that our book, Columnar Structures of Spheres, is finally published since last Friday. Links to Amazon and other resellers can be found in the description below. In my previous video, which you can actually find up here, I introduced you to columnar structures of spheres, which occur when spheres are being packed densely inside cylinders. I presented you how these structures can be created in simulations and in simple experiments. But during my PhD at Trinity College Dublin, this topic was given a new spin by a group from South Korea. Lee et al. Came up with a new, very promising experimental method to create columnar structures that involve rapid rotations. In this video, I will introduce you to this novel assembly method and explain the physics behind it. Inspired by their work, we performed analytic energy calculations that lead to the prediction of interesting new features for such structures. By comparing the analytic results with finite-size simulations, we did not only corroborate our theory, but also extended our results by rediscovering a structure that we already encountered in my last video. The group around Lee et al. Came up with a novel assembly process for columnar structures displayed in this video here. The experiments involved rapid rotations and polymeric beads in a fluid, which essentially behave like hard spheres. We can observe that these beads are being pushed towards the center where they form a columnar structure. They recorded the experiments with a high-speed camera since the actual rotational speed is around 3000 rpm. And apart from the defects at the wall, you can actually see a nice homogeneous structures in the tube right here. We already encountered such a structure in my previous video where we called them uniform structures. But before we go into detail about the results, let's have a look at the mechanics behind this assembly process. So what did Lee et al. Do? They placed spheres together with a denser fluid inside a rotating lathe. In a denser fluid, it simply means that the spheres are floating. The centripetal force then pushes the dense fluid outwards and the spheres towards the central axis. And this leads to rotational energy that traps the spheres inside a cylindrical harmonic potential. And regarding their results, they found homogeneous structures or binary mixtures depending on rotational speed and the number density. A homogeneous structure is a packing of a single type that fills up the entire tube, and we're actually quite familiar with these structures already from my previous videos. There we called them uniform structures. But the binary mixtures are a new type of structure that differ from the previous structures by this little interface right here. Based on this knowledge, we developed analytic energy calculation for such rotational columnar structures but using soft spheres. And I will only outline here the basics, but for details I'd like to refer to a new book that was just published recently. You'll find a link to order in the description below. The calculations are performed in two steps. First, we calculate the energies for the homogeneous structures. And this is given by the rotational energy and the interaction energy of the soft spheres. The rotational energy depends on the radial distance r squared and the rotational speed omega. And for the sphere interaction, we use the same soft sphere model that I already discussed in my previous video. So within this model, the spheres are allowed to overlap, but then they behave like repelling springs. So the energy then depends on the overlap squared. And the sphere interaction term is then just a structural constant. And thus we can reduce the dependency of the total energy to only the radial distance r. And then to get a stable structure configuration, we can minimize the total energy with respect to just one variable r. The energies of the binary mixtures can be obtained via a technique that's called Maxwell construction and also known as the common tangent construction. So let's say these two curves here represents the energies of the homogeneous structures. The energy of the binary mixture is then given by the common tangent between the two adjacent homogeneous structures. And an assumption that we make here is actually that the structures are infinite and the interface energy is neglectable. We use these two techniques then to calculate the energies of stable structures at a constant rotational speed versus the inverse number density. All colored curves that you see in this plot right here represent the energies of homogeneous structures, and all the black straight lines are the common tangent for the binary mixtures. The homogeneous structures are only stable within the colored stripes, whereas we predict the binary mixtures for the white areas since their energies, given by the common tangent, is lower in this area than for the homogeneous structures. And when we repeat this now for varying rotational speed omega, we can map out a phase diagram. It is plotted here with the rotational speed on the vertical axis and the inverse number density on the horizontal axis. The colored regions display again the stable areas for the homogeneous structures, and our white regions are again binary mixtures. And I love to say it is packed with great features, but the most interesting ones are these two paratectoid points. And what we observe in general is the range of homogeneous structures increases with the increasing omega, except for these two achiral homogeneous structures. They actually vanish in what's called a paratectoid point. At these points, the two structures vanishes together with the adjacent binary mixture, and a new binary mixture of next year's homogeneous structures emerges above them. And at 0 omega, we actually make contact again with the hard sphere limit. And I plotted here the experimental results from the Korean group who used hard spheres in their experiments. So in order to verify these analytic calculations, but also extend them in the direction of the lathe experiment, we performed finite-size simulations that are based on energy minimization. We used periodic boundaries to imitate an infinite column, but the simulations were limited to a finite sample size of 24 spheres. The simulation is based, similar to the analytic calculations, on total energy minimization. The total energy in our simulation also consists of the rotational energy plus the soft sphere interaction. But now we minimize with respect to all sphere positions and the twist angle alpha. That means we leave here a much higher degree of freedom during the minimization process. And for the minimization, we use again the Basin-Hopper method to find the global minimum. And we already used this method to find optimal packing of spheres and cylinders in my previous video. For comparison between the analytic calculations and the finite-size simulations, we performed finite-size simulations for a fixed rotational speed and a variational number density. The simulation energies are plotted here now as the red dots. The minimized energies for the homogeneous structures calculated analytically are the colored curves, and the common tangent for the binary mixtures are displayed here in black. And we can see the simulations are spot on for the homogeneous structures, but there are variations for the binary mixtures. These variations can be explained by the finite-size effect in the simulation. The energy in the simulation is higher than the analytic calculations due to a structural interface. And actually it's that much higher that we predict a completely new structure in this area, a line step structure. Just to reiterate the explanation of a line step structure from my previous video, this is a contact network and the structure is defined by loss of contact as displayed on this example structure right here. However, the line step structure vanishes and the deviation in the energy becomes smaller with increasing system size. Thus, we can ascribe this interesting feature to finite-size effect. But for more information on the analytic calculations as well as the finite-size simulations and the comparison, I refer here again to our new book, Columnar Structures of Spheres. In my next video, we will investigate one particular structure in closer detail with the technique described in this presentation. So what you see here is a chain of polymeric beads inside a rotating fluid. The chain is actually aligned in a linear row where the number of spheres is commensurate with the length of the tube, but it encounters this type of buckling behavior under compression. So stay tuned for part 3.